This lecture introduces separable differential equations. First, let's look at a motivating problem. If we want to solve the differential equations here, dy over dt equals to e to the t divided by 2y minus 2. Remember, in calculus 2, we learned how to solve this differential equations. What did we do? Let's rewrite these equations. And then since we have y, right, and t, we can separate y and t on both sides. I move 2y minus 2 here, dy equals to et dt. And then from here, we can integrate both sides to get, let's say, 2y squared over 2 minus 2y, right, equals to e to the t plus c. This is gone, so the final solutions is 2y equals to e to the c plus c. So this is the solutions of this differential equations, and you can see that this solutions here is not written as an explicit solutions because you cannot solve for y by itself. So this is an implicit differential solutions. It's not an explicit solutions. All right, so we know how to solve this differential equation, and we can see that if you have a differential equation where you can separate y function and t functions, right, on both sides, then you just integrate both sides with respect to y and respect to t to solve for these equations. So this is an example of a separable differential equations. And in general, a differential equation is called a separable differential equation is an equation in this form. The form where you have dy over dt equals to a functions of t multiplied to a function of y, right? So you can solve for this differential equation, separable differential equation by, divide both sides by the function h of y in terms of y, and you move it to both sides. To the other side, right? And you move the dt to the right side so you can integrate both sides. But then before you want to solve for this equation, you wanna maybe first try to find the equilibrium solutions first. Again, equilibrium solutions are the solutions when dy equals to dt equals to 0, right? You can find the equilibrium solutions by solving h of y equals to 0, okay? Because you cannot divide both sides by h of y when h of y equals to 0. So find all the equilibrium solutions, and then after that, you can divide both sides by h of y, and then integrate both sides with respect to y and t, respectively, to solve for the differential equation. Okay, well, let's do some practice. Here, look at the first example here. You can see this is the differential equation of y in terms of x, and we can see that at first y and x are not separately. Then we can do some algebra manipulations in order to convert this differential equation into the separable differential equation form. So I move x squared to the other side. And then you can see that I can factor the x squared out. Okay, now we have dy over dx on one side. We have a function of x and we have a function of y, and they multiplied together. Okay, well, the next step is we move this functions of y to the left side, and then we move dx to the right side. Okay, and you can see that at this point we can integrate both sides. Okay, then that will equals to 1 over y squared plus 1 is the integrate of 1 over y squared plus 1 dy would be arctan of y equals to xq over 3 plus c. This is the solution to this differential equation. All right. And if you want to solve for y, in this case, you can, because you can apply, this is arctan, right? You can apply a tangent to both sides. So then y equals to tangent of x squared over 3 plus c. This is a general solution to this differential equation here. All right, let's go to the next example. So the next example, you have, well, dz over dt, that means the function of z, like the z function in terms of t, and you have, this is the right side. At first, this functions here is a function in terms of z and t are not a product of the two function in terms of t and function of term of z. But then again, we want to do some algebra manipulations to form the right side into a product of the two functions. So it's going to be 1 minus t, and z is a common factor, minus z, right? And then take 1, and then minus t. And then 1 minus t and 1 minus t is the common factor, then 1 minus z. Okay, so now we have dz over dt equals to 1 minus t times 1 minus z. Now it's the right side is a product of two functions. One is function in terms of t and the function in terms of z, and now we can separate them. So then I move 1 over z to this side, right? dz over 1 over z equals to 1 minus t times dt. And again, you integrate both sides to get the integral of 1 minus z dz is natural log of 1 minus z. And the integral of 1 minus t is t, right? Minus t squared over 2 plus c. All right. Now, if I want to solve for z, I can try to solve for z. So remember, we have the absolute value here just to make sure that 1 minus z has to be positive. Okay. Well, equivalent to, this is the same as a 1 minus z equals to e to the t. I forgot this one here. It should be negative 1 minus z. And then, because this is negative z, so you should have a negative here. And then 1 minus z equals to e, and my 2 negative, I should use a different color. Negative t minus t squared over 2 plus c. Okay. And then this equivalent to, so I can just get rid of the absolute value right now, and then z will be equals to c, and e to the c e to the constant is a constant, so I can move it out, right? And then z over there, and I would have, I move z to the right side and I move this to the left side. So z equals to 1 minus c, big C, e to the negative t plus t squared over 2, which is my general solutions to this differential equation. Yeah, you just do some algebra here, right? You get rid of the absolute value here. And then you solve with z, moving it around to get, this is your solution. Okay. All right, so again, once you can identify a differential equation as a separable equation, the next step, you just move, the dependent variable to one side and independent variable to the other side and do the integrations to get your solution.